Okay, this is the second hour of Physics 1A for, what is today? It's not going to cover. March 8th, I think. So we are going to continue talking about one-dimensional motion, and the next topic is acceleration. All right, so acceleration can be thought of as the rate at which your speed changes. Okay, so you experience acceleration when, for example, you're sitting at a stop sign. Your car is at rest, so it has a speed of 0. And, this isn't even quite right. It's the rate at which velocity changes, actually. Sorry. You're sitting at a stop sign. Your speed's 0. And you hit your gas, and then you move away. So your speed starts to increase. And that speed increase is read out on your speedometer. Your speedometer goes up from 0 to 10 to 20 to 30 miles an hour or whatever. And the rate at which that speedometer is going up is your acceleration. The rate at which your speed is increasing. Acceleration can be positive or it can be negative. It's negative when you slow down. It's positive when you speed up. We don't very often we don't use the term deceleration really in physics. We just use the term acceleration and say, if you're speeding up, it's positive. If you're slowing down, it's negative. But yeah, just the rate at which velocity changes. In one dimension, that's going to be equivalent to the rate at which your speed changes mostly. But in 2 dimensions, when your velocity changes, such as when you turn, you're also going to accelerate. Something I'm sure you've experienced when you take, for example, like an exit ramp on a highway. As you go around that exit ramp, you can feel your body accelerate because as you're turning, your velocity vector direction's changing, and that's also a type of acceleration. Okay. But in this particular chapter, it's just going to be about acceleration happening as a result of kind of the magnitude of your velocity changing. So how do we define it? So just like we did before, we can define average acceleration by finding the change in your velocity vector. Now, this v right here has to be instantaneous velocity now. It has to actually be your velocity at a moment in time. So that's average acceleration. And, we could give an example of this. For example, if I have an object like a car, and let's say that it's moving along the road and it starts off with an initial velocity. So I'll use this v0, v0 for initial velocity. Let's say it's moving with an initial velocity that's equal to 10 meters per second. And let's say that it travels along some road, and then at some later time, maybe like 10 seconds later, it has a final velocity of, say, 40 meters per second. And if you want to calculate the average acceleration, if you say that the initial time is 0 seconds, let's say, and the final time is 10 seconds, then you can find your average acceleration, right? By just taking 40 minus 10 and then dividing by 10 minus 0. Put the units on the outside. So 40 minus 10 is 30. Divided by 10 gives you an acceleration of 3 meters per second squared. All right. So the unit we use for acceleration could be meters per second squared, it could be feet per second squared, but it's going to be some type of a distance divided by second squared. And to say that you have an average acceleration of 3 meters per second squared is to say that if you start with a speed of 10, then let's say that this acceleration happened to be constant in this case. Let's say that you're accelerating in a constant way from 10 to 40. How fast would you be going after 1 second has elapsed? You start at 10 meters per second. I say you're accelerating at a rate of 10 meters per second every second. You'd be going 13, yeah. After 1 second, you would have gained 3 meters per second, right? How fast would you be going after 2 seconds have elapsed? So you start at 10. The first second you go from 10 to 13. The second you go from 13, you add another 3. You're at 16. So that's what acceleration does for you. It tells you how many meters per second you add every second, right? That's what it means. So sometimes the way that this might be written is like this. It might be written as 3 meters per second, basically. Because that's the rate part of it. It's like how fast is the velocity, which is 3 meters per second, changing? Well, it's changing at a rate of 3 meters per second every second, right? Okay. All right. Now, something we can talk about with acceleration to see if you have a kind of an understanding of like what it means, basically. So think about the following situation. So I'm going to make a little table here. In the first column, we're going to have velocity. In the second column, we're going to have acceleration. And in the third column, we're going to ask the question, speeding up or slowing down, basically. So let's say that your velocity is positive, okay, and your acceleration is positive, right? So your velocity, let's say, is 10 meters per second, like over here, and your acceleration is positive 3 meters per second squared. Is your car going to speed up or is it going to slow down? Yeah. Pretty obvious, right? Okay. What about if your velocity is positive, but your acceleration is negative? So same thing here. Maybe initial velocity is 10, but we say your acceleration is like -3. You'd go from 10 meters per second. What would your next speed be? You're slowing down, right? Exactly, in this case. Right? So if this, for example, was positive 10, and this was -3 meters per second squared, let's say, then after 1 second, you'd be at 7 meters per second squared. After 2 seconds, you'd be 4, and then 1. And then after that, your velocity would start to become negative again. So let's look at that scenario. What happens when your velocity becomes negative and your acceleration is still negative? Are you going to be speeding up or slowing down? So let's say your velocity starts off at -5 meters per second and you experience an acceleration of -2 meters per second squared, then you are speeding up, like everyone's saying. So here your speed goes up, right? Because so you still understand the difference. Like velocity could be negative, but your speed is going upwards, right? So if you have a velocity of -5, but an acceleration of -2, then in the next second you'd be at -7, and then -9, and then -11, and so on and so forth. Okay, one final possibility, which would be that your velocity is negative, but your acceleration is positive. What's happening now? Speeding up or slowing down? Slowing down, yeah. So you get kind of an idea that when one's positive, when they have the same sign, you're speeding up. And when they have opposite signs, you're slowing down, right? So looks like the sign rules for adding and subtracting. That's all that's going on. Absolutely, Paige. But we're thinking about like concepts now, not just numbers. Velocity is like how fast you're traveling in terms of meters per second. Acceleration is meters per second squared. All right, there we go. That's acceleration. Of course, the next thing to do is to define instantaneous acceleration. So let's just define that right here real quick. So that's our definition of average acceleration right there. And it turns out that most of the things we do in this class, well, I'll stop. So instantaneous acceleration. For this, we'll just use the symbol a sub x and say that this is going to be equal to the limit as delta t approaches 0 of the change in your x velocity, v sub x means x velocity, divided by time, or the other way to write it is as the derivative of your x velocity with respect to time. So that is instantaneous acceleration. Now, if your acceleration is constant, then these two things are the same, right? And that's what most of the problems in this class are going to be about. You're not. It's going to be pretty rare that you have a situation in which the acceleration is changing, at least for the first 6 chapters or 5 chapters. After that, we'll learn how to handle situations with non-constant acceleration. Okay, but let's talk about constant acceleration, because that is a very specific case that we can handle really well and will help us to get through a lot of problems and things that we can analyze. So with constant acceleration, that means your acceleration is constant. It's just a flat number. Like this would be an example of a constant acceleration, right? In that case, your average acceleration and your instantaneous acceleration become the same thing. They just become maybe just some a or something like that. Okay? Constant acceleration. Now, why would we care about constant acceleration? Why do we care about constant acceleration? So, free falling, exactly. There's a lot of scenarios where constant acceleration shows up in nature. And I'll give you a couple of examples. If I take a ball and I hold it above the surface of the earth and I release it, whether I throw it upwards, downwards, doesn't matter. Release it from rest, doesn't matter. This ball will tend to fall down toward the earth with an acceleration that's equal to, usually written like this, negative 9.8 meters per second squared. Or that acceleration can also be written as negative 32 feet per second squared. Now, why do I write negative? Well, normally we kind of tend to want to define up to be positive, but you don't have to do that. So as long as I define up to be positive, then we would say that this is what we call free fall acceleration. And both of these are usually symbolized with the letter g, where g represents gravitational acceleration, right? So that's an example of constant acceleration. An object near the surface of the Earth tends to accelerate at this constant rate, something I'm sure you saw show up in your previous physics classes. And sometimes what we'll do for this one right here is we'll just approximate that it's equal to 10, because that's a number that's easy to deal with. Because if you start with a number like 10, what you can say is that if I take a ball and I let it start with an initial velocity that's equal to 0, and I let it fall to the ground, so let's say that the ground right down here, then what I know is that after 1 second has elapsed, how fast will the ball be falling if you drop it from rest? Yeah, 10 meters per second. And then a second later, it will have fallen quite a bit farther, actually. So this would be the 2-second point. But how fast is it going then? After 2 seconds have elapsed. Yeah, 20 meters per second. So the way we think about free fall is you add 10 meters per second for every second the ball is falling. After 1 second, it's at 10, and after 2 seconds, it's at 20 meters per second. After 3 seconds, it'll be at 30 meters per second. All right. Now, the distance that the ball actually falls, well, it's not going to be like that, actually. It's actually going to be the case that if it falls 1 unit of distance in the first second, it's going to fall 3 times as far in the second, and it'll actually fall 5 times as far in the second after that. But before we get into those details, we're just trying to understand constant acceleration and why it matters, right? Now, the other thing about constant acceleration is not only does it show up in free fall situations, but it also shows up when you have an object that rolls down a flat surface. This is something that's figured out by Galileo. So Galileo was the first person to really come up with a truly accurate calculation for the speed of gravity. In fact, Galileo is somewhat famous for supposedly doing some kind of a demonstration to the public where he took 2 different balls and he dropped them from the top of the Leaning Tower of Pisa, and one ball was really heavy and one ball was light, and he kind of proved that they both hit the ground at exactly the same time, which may seem obvious to you, but if I ask the question this way, like, take a ball that's 10 kilograms, take another ball that's 1 kilogram, and drop them from the same height, what do you all think? Do they hit the ground at the same time? Okay, maybe you all know. I don't know. Do you all know that they hit the ground at the same time? Well, in Galileo's time, nobody nobody knew that because what Aristotle had said, he's the person that came before them. He said that heavier objects fall faster, and the example he gave, which is a bad example, he said, a rock falls much faster than a feather, right? That's true. A feather's like really light, and it gets caught by like wind currents, so it falls much more slowly than a rock. But if you take out the kind of air resistance portion of it by using two similarly shaped objects, like for example a basketball and a bowling ball. Basketball is obviously way lighter than a bowling ball, but a bowling ball will hit the ground at the same time as a basketball. It doesn't matter how light it is, unless there's just a huge gust of wind that shows up that blows the basketball away, right? So Galileo did that, and Galileo was kind of the beginning of using actual experimental methods to test things, stuff like that, right? And he was the first person to actually calculate the acceleration due to gravity. Does it matter with distances as well for that, or will it always be this? It matters how high you drop it from, for sure, Paige. Yeah, if you drop one at a much higher height, you have to drop it from the same height, basically, right? Okay, but Galileo calculated the acceleration due to gravity, but he did not calculate the acceleration due to gravity by standing on top of the Leaning Tower of Pisa and timing how long it took for balls to hit the ground, because as tall as that object is, you could compare it today as probably standing on the top of like maybe a 10-story building, right, and dropping a ball. If you go to the top of like a 10-story building, just think of a really tall building that's near you, pick anything, and you drop a ball, it actually won't take very much time for that ball to hit the ground because gravity is really fast. So gravity is so fast, in fact, that it's very, very difficult to actually calculate how fast it moves. But what Galileo figured out was, it turns out that you also get constant acceleration if, for example, you take like a marble and you roll it down an inclined plane. It doesn't matter that there's an inclined plane here. As long as it's roughly flat, then the rate at which that marble goes down the plane will also be constant acceleration. That's what Galileo figured out. And he used this as kind of a cheat to be able to calculate the acceleration due to gravity. So he used these really long inclined planes that had grooves running down the center of them, and he would place steel balls on these inclined planes, and he would time how long it took for the golf to go from one end to the other, right? Now, in his time, there weren't really that many good like devices that you could use to keep time. So what Galileo did was he actually timed things with his pulse. He used his heartbeat to calculate how long these balls would take to go down, and he did tons of experiments, as you need to do when you have a stopwatch that is as inaccurate as your heart. As you all know, the rate at which your heart beats, right? It's not constant, right? If you get excited, your heart starts to beat a lot harder. I know sometimes I'll be watching like streams on Twitch, and sometimes I'll watch people play poker, and a lot of them have like a heartbeat monitor on them. And you can see their heartbeat goes like crazy when they start bluffing and stuff like that, right? So, and you also know that if you go out for a run, your heart's going to beat harder, right? So Galileo, nonetheless, was still able to come up with a very, very accurate number for the acceleration due to gravity, and to prove that it was constant by doing these accelerations and timing things with just his pulse, which is pretty impressive. I mean, it's really impressive, to be honest, because if we were to go into the lab and we did a lab where we calculate the acceleration due to gravity, you'll find that even using modern stopwatches, it's really hard to get this number. And I think Galileo's number was something like 9.7. So it's pretty close. It's like, really close. So anyway, that's almost 1% within, the modern value. So yeah, so constant acceleration is interesting because not only does it work for objects that just move in a straight line like this, it also moves for objects that roll down surfaces that are an inclined plane. And it also works for things like cars, where you could say like, oh, suppose that you have a car and you accelerate at a constant rate. You can design problems like that, or bikes, or whatever you want to do. So that's why we care about constant acceleration. It kind of shows up in nature all around us. We can also say that the Earth, as it moves around the sun, and we'll get to this much later when we talk about circular motion, it is also undergoing constant acceleration. The moon, as it moves around the Earth, is undergoing constant acceleration. So constant acceleration is really important. It just shows up all over the place. And when we use constant acceleration, starting with, for example, our average acceleration equation right here, it turns out we can write down 5 equations that can relate the velocity, position, time, and acceleration all to each other. And so that's what we want to do. So we'll start with the definition of average acceleration. Our acceleration is now just going to be written as a. And before we said that that was equal to basically the change in velocity, or what this is often written as, final velocity minus initial velocity divided by the time interval. This allows us to write an equation. If we multiply the delta t to this side right here, you get a times delta t is equal to final velocity minus initial velocity. And from here, we can either leave the equation like this, or we can write it in another way. And usually the way this is written is like this. Final velocity minus initial velocity. Whoops, nope, my bad. Usually write it as final velocity of an object is equal to the initial velocity of the object plus the acceleration multiplied by delta t. So that's an equation we're going to use pretty frequently in this class. Keep in mind that this equation only works for constant acceleration. So the acceleration has to be constant for this to be true. All right, let's take this equation and let's ship it over here to the right so we can have a list of equations when we're done. This equation says the final velocity of an object minus the initial velocity of an object is equal to acceleration times the time interval. Should be a pretty familiar equation to you. In fact, whether you knew it or not, you were using this equation when I asked the question. Suppose you start from 0 and I give you a constant acceleration of 10, and I say, how fast is the object moving at 1 second? Well, you just take 10, whoops, sorry about that. You just take the acceleration, which was 10, times 1, plus 0, and you get 10. Or 10 times 2, plus 0, and you get 20, right? So you already inherently kind of understand, I think, what this equation says, if you understood how to figure out the speed of the falling object. Okay, so we need some more equations here. And to get the rest of them, we are going to have to rely on what we said before about displacement and average velocity. Okay, so in the previous section, when we were talking about average velocity, we wrote down an equation that looked like this. We said average velocity was equal to displacement divided by time, right? Now, there's another way you can write average velocity. In the special situation where acceleration is constant, okay? Let's draw a graph, because I think it helps to understand what I'm about to say. Ooh, is that something I can draw? Wait, how do I make it like that? There we go. All right, so let's say we got a graph like this here. How do I make it bigger? Just like that. Okay. Let's say that I wanted to plot a scenario in which an object was moving with constant speed, okay? And I plot up here velocity and I plot over here time, right? And I want to think about, what is a velocity versus time curve? What does it look like if I'm talking about constant acceleration? What's it going to look like? Maybe it makes sense to, it's going to be linear, right? Let me draw a couple lines here. What if I drew a straight line like this? That's not what I wanted to do. We'll use an actual straight line. So what if I drew a straight line across my curve like this right here? Completely flat. What would the acceleration be in this situation? 0, because it's the slope of the curve, right? So now we take that same curve and we tilt it a little bit. Is the acceleration positive or negative now? It's positive, yep. And then if we flip it around, hopefully you guys understand that if the velocity is going down over time, its acceleration is negative now, right? Because you got a negative slope. Okay, so we now know that a curve like this represents an object with a constant acceleration, right? Constant acceleration, constant slope, right? And if I pick 2 points on my graph, so let's say I pick a point, let's say right here, pick a point right here, and let's say that this point right here represents my initial velocity vector, which we would see it over here. And this point right here represents my final velocity vector, okay, which we would see hit the curve like right here. if I want to find the average velocity now, okay, if I want to find the average velocity between these 2 points right here, and maybe I pick some numbers to make it more clear what's going on. Let's say that my initial velocity vector is, let's use 10 and 50. Let's say our initial velocity is 10, and my final velocity is 50 meters per second. Can anyone tell me what the average velocity between those 2 points would be? What would the average velocity between those 2 points be? And I want you to figure it out, Andrew, without knowing what delta t is. That's the key to this. We need to figure this out without knowing delta t. I'm seeing some people say 30. How did you get 30? Where did 30 come from? I'm not saying it's wrong. I'm just asking where it came from. How'd you figure it out? Yeah, you summed the velocities and you divide it by 2. Exactly. Exactly. So if I have an object that's speeding up like this and it goes from 10 meters per second to 50 meters per second, then the average velocity should be right smack dab in the middle, right? That should be the average velocity, right in the middle right there. And you can calculate it. I'm going to write this over here on the left by doing exactly what I think it was Chris said. You can take the final velocity of your object plus the initial velocity of your object, and you just divide by 2. Just do a normal old average. Now, this won't always work. It will only work, again, with constant acceleration. Okay? If the object is speeding up in some kind of way, this is no longer going to be true. But for an object that does this, that is your average velocity. So you just take 50 plus 10, divide by 2, 60 over 2, you get 30 meters per second. That's your average speed. Does that make sense? So now what we can do is we can look at the right-hand side of this equation, because now what we have is something that will help us. Here, I'm going to take this whole thing here, and we're just going to move it off to the side, so we don't really need it. So now that we know that that's one way we can define delta x over delta t, we can now write a new equation, and it'll look something like this. So I'm just going to move the delta t to the right-hand side. It's the only thing that I'm going to do, and say delta x is equal to 1/2, this is usually how it's written, of the final velocity of an object plus the initial velocity times delta t. These equations are usually not written with vector symbols, but I'm writing them like this because in one dimension it certainly works. And keep in mind that these things can be positive or they can be negative. Okay, I caught the 2 there, I didn't want to do that. Copy this one and put it over here. May make it a little smaller. So that's our second equation. And in order to get the other 3, we simply need to start eliminating variables between these 2. All right. And these equations have a name that you're probably familiar with. These are known as the kinematic equations. So, what do we have left? Okay, so let's try to get rid of final velocity first. So for this, what we'll do is we're going to take this final velocity definition and plug it in right there. Okay, do a different color. So now what we're going to have is delta x is equal to 1/2 of final velocity, which is this, oop, I left off 1. Oops. We can just go undo. So there we go, plus the initial times delta t. Okay, so we got that equation. All I've done is basically just sub in this term here from our final velocity definition for final velocity here. So just v0 plus at goes right in right there. And you get that. And now we multiply out in group terms. So what we're going to have is there's going to be a term that's going to be 1/2 v0 plus v0. So that's 2v0 divided by 2. which is just v naught, and it's multiplied by delta t over here, plus we're going to have a 1/2 times acceleration times delta t, or 1/2 at squared. So that is our third equation. And we'll write one more down. There's a fourth equation that we won't derive, but I'll tell you what it is. So that is our third equation. I think this is the one that gets used like the most frequently. All right. And I guess we want to eliminate. So this one doesn't have a delta x in it, this one doesn't have an a in it, and this one doesn't have a final velocity in it, so we need one that does not have a delta x in it. No, delta t. We want to eliminate delta t now. All right, so we'll do that like this. Look at this equation here. This equation says, if I rewrite it, that delta t is going to be equal to v final minus v initial divided by the acceleration. Dividing by a vector is wrong. I shouldn't be writing this. This is the part where we run into problems with this vector notation stuff. But we'll just leave it for a moment like this. And I want to take that delta t and I want to plug it into right there. Okay. So what we're going to get is delta x, that delta x is equal to 1/2 of v final plus v initial. We're plugging in this term right here. Okay, and now I can get rid of the fact that this is in the denominator if I want to. I'm also going to say that the type of multiplication that we're going to be doing here is a dot product. Okay. So this acceleration vector, we're going to move to the left-hand side. Yeah, this is where I got to get rid of these vector symbols. This is just getting to be too much. There's just too much here that's wrong. So we're just going to get rid of all the vector symbols. Even saying that this is a dot product, I start to see some problems, actually. So let's just not worry about the vector symbols for the moment. Did I delete too many things? This was an A. I think we're good. So what we're going to do now is... Oh, delete that last vector symbol right there. Okay. So next thing we're going to do is take this 2 and this A and move it to the left-hand side. So it'll be 2A times delta x equals... And then we have VF plus V naught times VF minus V naught, which is something that you probably recognize as a difference of squares. It can be written like this. You can multiply it out if you want to. You'll get VF squared minus V initial squared. And then that equation can be written as our last equation right here if we solve for VF. The normal way this is written is VF squared is equal to V initial squared plus 2 times the acceleration times delta x. Yeah, none of these can be vectors now because VF squared and V naught squared are no longer vectors. So A times delta x can't be a vector either. And those are the normal 4 kinematic equations. The way I like to distinguish between them, there are a total of 5 variables in these equations. There's delta x, there's acceleration, there's the 2 velocities, initial and final, and there's time. Those are the 5 variables that show up in these equations. As long as you know 3 of the variables, you can find a 4th one, right? Because there's 4 variables here, meaning you need to know 3 of them. You know, oh, this should have been, my bad. This should be V initial right here. Sorry about that. If you know 3 of the 3 of the velocity, 3 of the variables, you can find a 4th one, right? So the way that I like to think about these is by what is missing from the equation. So the first equation here, which of the 5 variables is missing from the first equation? The green equation right here. Which of the 5 variables? It's x or just delta x, right? So I'm going to write no delta x. Let me make this a little skinnier. Which variable is missing from the second equation? acceleration. Third equation, final velocity. This last equation is time. Okay. Now, does this mean that you can't have a displacement in the first equation or that you can't have acceleration in the next equation? No. This equation right here applies to systems where they're accelerating, okay? You don't want to use this equation for constant velocity, okay? You can, but your final velocity and initial velocity are the same. So just keep in mind that in addition to these four equations right here, you also need your uniform velocity equation. Let me write that one up here just in case it's unclear. This is the thing that you learn probably super early on in school when you're learning about rates and speeds and stuff like that. For uniform velocity, this is your equation. Delta x is equal to velocity times time. That is your uniform velocity equation. And the second equation right here reduces down to that if you just make Vf equal to V naught, right? Because then you'll have V plus V divided by 2. 2V over 2. You get the same equation. But okay, just because there's not an acceleration in this equation, it's still talking about constant acceleration, right? Because we used constant acceleration to derive it. Okay, so all of these equations, the kinematic equations, refer to situations in which you have constant acceleration. It's the only time you can use them, right? So there is one equation we're missing, right? What would the final equation be missing? Which variable's not listed here? No, time is the last equation. Sorry, I'm saying we need a fifth equation, right? We need a fifth equation here. What would the fifth equation be missing? V initial, exactly. So if you want to figure out what that one is, you can. You can use these equations here and you can just basically eliminate final velocity. So what would that look like? Well, it's going to look just like the third equation here. It's going to be delta x is equal to, and now it's going to be, I think this is the equation, VFT, and instead of a plus sign, you get a minus sign. Okay, but derive it yourself. I'm pretty sure this is what it is, though. I can never remember if the minus sign goes here, if the minus sign goes here, but I'm pretty sure this is the right way to do it. All right. So those could be considered your 5 kinematic equations that we're going to use to solve some problems. And since we're coming right up to the top of the hour here, I think this is as good a place as any to just go ahead and stop. And then we can spend the last hour, and then we can spend Wednesday solving hopefully, all the problems that I have set up here for you. So before we do that, let's just take a few minutes. Does anyone have any questions? You don't need to write these vector symbols everywhere, by the way. You don't have to do that. In fact, what we'll see in the next chapter is it probably makes sense not to write them, because when we have things move in 2 dimensions, all of these equations will be scalars. Everyone remember these equations? Do you remember how to use them? I'll tell you what we'll do. I'll throw up the first problem we're going to work on. Maybe the first 2. Can I pick both of these up? Okay, cut. Paste. So if you want to try to do these 2 problems, yeah, go for it. Let's see if I can get all of these guys and copy them down here or something. So, yeah, try to do these 2 problems during the break, and then when I come back, we'll try to solve them. Zoom out a little bit. These 2 problems we'll do first. We should easily be able to finish this today. You remember from high school, I believe we used some of them in the class before this, used for a good month and a half in 2A, yeah. We won't be spending 2 months on the kinematic equations like is usually done in 2A or in high school, but probably 2 weeks. Because we'll do 1 week of 1 dimensions, 1 week of 2 dimensions, which will also use the kinematic equations. And then after that, you have to be very careful about when you use these. Because when can you use them? What kind of problems can we use these on? What has to be true? Constant acceleration, exactly. So just keep that in mind. Keep that in mind. Before you're going to use these equations, keep in mind it has to be constant acceleration. Because once you get good at solving these problems, you're going to be tempted to want to treat every problem like something like this. But you can. So, okay, let's take a break. It's 4 o'clock. Take a break till 4:10.